Now let us go to exponential functions. The parent function of the exponential function is equal to y is equal to b raised to x. This is the most basic function for an exponential function. And the graph of an exponential function for the parent function y is equal to b raised to x would be something like this. Okay, and in here the example is given, which is y is equal to 2 times 1.2 raised to x. Well, an exponential function is in terms of b raised to x, where our b is a constant. So b is an element of real number, and your b cannot be equal to 1. Okay, because if it's 1, then there's no sense. 1 raised to x is just 1. Okay, so the general equation of an exponential function is in the form y is equal to a b raised to x. Again, a is in here, meaning that the sign of your a will affect the graph of our exponential function. So a can be greater than 0, or a can be in between 1 and 0, but definitely a cannot be equal to 0, okay, which is already defined here. So actually no need to state this. Okay, and of course a could be also less than 0. Okay, and a greater than 0 is actually also here, so I don't need to postulate the middle condition. Okay, so in the given exponential function y is equal to 6 times 0.7x, the graph would be like this. Okay, with the y-intercept here, and it has an asymptote at this x or y is equal to 0, or the x-axis. And the transform function of the exponential function is in the form y is equal to abx plus c. So there is a vertical translation. Okay, vertical translation. 3 or c units upwards. And what else? We have a dilation also here. So a dilation, okay, or a dilation by factor a. Vertical dilation by factor a. Okay. Okay. Now let us investigate the individual graphs and individual exponential functions. So let's move on. Let us begin with the most basic. So the parent function y is equal to b raised to x. So in here we have, or actually this one is already like the second one, but getting the most basic of it is actually taken from y is equal to b raised to x. So let us take this for example. Y is equal to 2 times 1.2 raised to x. So y is equal to 2 times 1.2 raised to x. So our b is 1.2. Okay, now we need the table, of course. And the the x and y values. Okay, and I'm going to indicate my independent and my dependent values, so x and y. And I'm going to choose x from 0 to 1, 2, 3, 4, 5. Let's say from 0 to 5. So let's have 0, 1, 2, 3, 4, 5. Okay. Please have your calculator with you. We're going to solve a scientific calculator. Okay, and we're going to solve the values of the y for specific values of our x. So if our x is equal to 0, then we will have 2 times 1.2 raised to 0. So we will get 2. Because our 1.2 raised to 0 is just equal to 1. So we will have 2 here. If our x is equal to 1, we would have, just replace your 0 as the exponents, replace it with 1. So we will get 2.4. So 2.4. And if we replace our x equals 1 by x is equal to 2, we will get 72 over 25 or 2.88. And if x is equal to 3, then we will get 430 over 125, so 3.5. And if our x is equal to 4, then we will have 4.15. If our x is equal to 5, let's see the difference. Then we will have 5.0, approximately 5.0. So let us graph those given points down. Okay. At first we have to arrange the position of our graph. So let's move it here. Let's get rid of those unnecessary lines there, or colors. Okay. So if my x is 0, then I have a y-intercept at 2. So I have a y-intercept at y equals 2. If my x is equal to 1, I have 2.4. So 1, 2.4. So it's almost in the middle of your 3 and 2. If my x is equal to 2, I have 2.88. So it's almost like 3. Okay. And if I have x is equal to 3, I have 3.5 as my y. So this is 3, 3.5. So it's here. If my x is equal to 5, or 1, 2, 3, 4, then it's 4.15. 1, 2, 3, 4, 4.15. So it's like here. And if I have 5, then it's approximately 5 also. So it's like that. Okay. So what is the shape of my graph? So let's connect all of the points. Get rid of this grid. And connect all of the points. I would love to connect it from here. Okay, so I have this graph. Okay, and so this is the graph of y is equal to 2 times 1.2 raised to x, where your b, or our b instead, is equal to 1.2. And our b is in this case greater than 1. So b in this case is greater than 1. Okay. And if b is greater than 1, you would notice that the graph is somewhat like this. And we will have an asymptote here at x is equal, or y is equal to 0, or the x-axis. So we will have an asymptote at the x-axis, or y is equal to 0. X-axis and y is equal to 0 are just the same. Okay? Now let us go to when your b changes. Okay, what if our y is equal to 6 times 0.7 raised to x? So in this case, our b, as you could see it, is in between 1 and 0. So what happens? What happens then? Okay. So we begin this by, of course, getting the table again. Okay, let's do it like this. One, 2, 3, 4, 5, 6. We have our x and y values. So this is my x and my y would be here. And I will get the same values for x that I used previously. 0, 1, 2, 3, 4, 5. Okay, now you have your calculator. Let's do it. So if our x is equal to 0, then just replace x with 0. So we will have 6 here. If x is equal to 1, then that's just 6 times 0.7. That's equal to 4.2. If our x is equal to 2, that would give us 0.7 raised to 2 equals times 6. So that will give us 2.94. If our x is equal to 3, so 0.7 cube equals 0.343 times 6. So that will give us 2.058 or 0.6. If x is equal to 4, so 0.7 raised to 4, that will give us 0.2401 times 6. That will be 1.44. If x is equal to 5, so 0.7 raised to 5 will give us 0.16807 times 6 is equal to approximately 1.01, or let's say 1.00. Okay, so graphing the coordinates or the points. So we need, of course, our grid lines. And okay, so let me make this also. Let us arrange first, okay, our axis. And set this. So this is our x, and this is our y. So make it somewhat colorful. Okay? So if our y or our x is equal to 0, we have 0.6. That will give us 0.6. So 0 and 6. We have a y-intercept at 6. Y is equal to 6. 1, 2, 3, 4, 5, 6. So we have a point here. Okay. And what is this? This is our x, or our y, I'm sorry. This is our y, and this is our x. If our x is 1, then it's 4.2. 1 and 4.2. 1, 2, 3, 4.2. So it's somewhere here. Here. Okay. If our x is equal to 2, then it's 2.94. Approximately 3. So 3, 2, 3. So 1, 2, 3. So it's approximately like there. If our x is equal to 3, it's 2.06. It's approximately 2. If our x is equal to 4, it's 1.44. It's in between 1 and 2. So it's almost in the middle. Okay. And if our x is equal to 5, we have 1. So it's here, approximately 1. And notice, okay, we're now going to connect all of the dots. Okay, now connecting all of the dots. Let me take off the grid now. Okay. Remember, we have a vertical asymptote, or I'm sorry, a horizontal asymptote at y is equal to 0. So we have a horizontal asymptote at y is equal to 0. So in this case, y, my pen is not working well. Okay, so it's y, it cannot be equal to 0. So meaning this curve here will just travel through the x-axis, or y equals 0, but it will not touch your x-axis. Okay, so this is the graph when b is in between 0 and 1. So remember this. Okay, what about when our b is greater than 1, but our a is less than 0? So as I've said a while ago, your a also affects the graph of the specific exponential function. So if your a is greater than 0, we notice that our graphs in the previous exponential functions are on the top of the x-axis. So it's either like that, or in the other case it's like that, but not touching your x-axis. What about if our x is equal to 0, or if your a, is less than 0? So what about that? So let's see. In this case, we have an example, and the example is just to clarify. Okay, y is equal to negative 3 times 1.06 raised to x. Notice that your b is greater than 1, but your a now is less than 0, because our a is equal to negative 3. Okay, so we begin again with forming the table. So we have a table. Okay, oops. Okay, so we will have a table, and the same values for x and y as we included in the x values and the y values in the previous examples. So let me have my x values here and my y values here. So if my x is equal to 0 up to 5, okay, then what are my y values? Again, we have a scientific calculator to rely on. So now we have negative 3 times 1.06 raised to 0. So if that's 1.06 raised to 0, then that will give us negative 3. If our x is 1, then that will give us negative 3 times 1.06, that would be negative 3.18. If our x is 2, then we would just simply change our 1 to 2 as the exponent, and we will have negative 3.37. If our x is 3, okay, then we'll just change our x to 3, and we will have negative 3.57. If our x is 4, then change our x to 4. From 3 changes to 4, we will have negative 3.79. If our x is 5, then we will change the x 4 to 5. We will have negative 4.01, or approximately 0, let's say. Okay. Okay, in this case we have to rearrange our positions for x and y. So let us reposition our x, ungroup this, and reposition your x. Let us put it here, and your y here. So now I'm going to label my x and y. So this is my y, and this is my x. Okay, what does our table say? So when our x is 0, then our y is negative 3. So we have a y-intercept at 0, negative 3. So where is that? 1, 2, 3. So it's here. If our x is 1, we have negative 3.18. So somewhere here. If our x is equal to 2, we have negative 3.37. Somewhere here. And 3, negative 3.57. And 3.79. And then 4 for 5. So it's approximately here. Okay, so what does this thing say? Now let us connect all of the points. Drawing a graph. So we could see that this is like a curve downwards, okay? So it's like this. It's curved downwards. Let's take off these grid lines. Okay, so our graph now is like this. So indeed, if our b is greater than 1, okay? So for this portion, our b is greater than 1, but our a is less than 0. And it gives us a graph that is like this. It's a reflection, okay? We have a vertical dilation with a factor of negative 3, and it is a vertical reflection across the x-axis, and the graph is concave down, and also it is decreasing. It's negative and decreasing. So it's going like that. So it's negative. Okay, now to summarize, we have the first condition. Our first condition is here. If our a is greater than 0 and our b is greater than 1, then we will get this graph as you see it. Okay, condition number 2, if our x or our a is greater than 0, and in this case b is in between 1 and 0, okay, and x or a, is greater than 0, then we will have this type of graph. Okay, I need the highlighter. Why am I having the pen? Okay, so the graph is like that. And number 3, if our b is greater than 1 but our a is less than 0, then we will have this graph. Okay, so as you can see, the graph changes for b is greater than 0 compared to b less than 0. Am I correct? And the exponential graph doesn't go through the origin for this for the 3 specific instances that we did. Okay, our b or our exponential graph has an asymptote at the x is equal to or the x-axis, or y is equal to 0. And therefore won't go through the origin. Okay, that's the common sense there. And notice how your graph changes for b greater than 0 compared to b less than 0, or b in between 1 and 0. So this is about exponential functions. On the coming lectures, we are going to discuss on the special exponential functions, as well as solving some problems related to the four functions mentioned: the linear function, the power function, the exponential function, and the quadratic function. So thank you, and have a nice day.